It's like one class. I'm not even it's bad. I'm not taking proud of it, but I did. I told myself, I was like, don't do what I did.
Okay. So we are ready to get going with our next topic, which is ultimately building up to something called the electrochemical driving force. So before we get started, we talked about membranes last time. We told you that ions are going to be important, and we've talked about where we have fluids. I want you to go ahead and draw yourself a little cell, and I want you to draw the cell with different concentrations of sodium ions on either cell of I want you to label where the ECF is, where the ICF is, what the solute is. I want you to label on your diagram what direction sodium will want to go. I want you to think about whether sodium can go in that direction. Can it cross the cell membrane? Why it can, why it can't. Give you a few minutes to do that.
Like, you know, it's really not that for us. It's just my brain can't handle all these math that I have to do correct. I always she was the one. What am I even doing? Like lost. Like I'm tired of just I know the first time like you guys were like, I don't feel like a lot of oh, yeah. I haven't been chat. I know how to do it. That was nice.
It's really great.
It has been since we got this.
Every day is a different day.
And then I was
Okay. So hopefully, at this point, this was quite doable, but we're going to walk through doing it together to make sure that we're all on the same page. Okay, so everybody started out by drawing themselves a nice little round cell. Okay, and we know that we're thinking about what sodium is. So sodium is our ion, our cat ion that we're thinking about. Okay. So we can label our locations. Okay, so our locations, let's pick green. Okay, so ECF is the extracellular fluid. That's our extracellular fluid. Extra means outside. So ECF, outside. ICF is intracellular fluid. So our ICF is inside. Okay, so those are two of our vocabulary terms essentially for this unit. And we know that our extracellular fluid can come in two types. We have the plasma and we have the interstitial fluid. Okay. And we said we had sodium, which is our solute because it's dissolved in the water. You can dissolve in the water because it has that charge on it and water is polar. So we have sodium both inside and outside the cell in different concentrations. So for your diagram, you might have chosen to have more sodium inside, or you might have chosen to have more sodium outside. Doesn't matter which. So we're going to go ahead. Sodiums. I'm going to draw lots of sodium outside my cell. Okay. So I'm going to give it a value too, in case you put some concentrations. Measure lots of things in millimoles. So let's say we have 60 millimoles of sodium outside. And we'll make up another number for the inside. Let's give ourselves 3 millimoles. When we're thinking about what direction sodium would want to go with the information that we have so far, so the things we've learned about up until now, hopefully we realize that what we've created here is a concentration gradient, a chemical gradient. So there's a difference in chemically how much sodium we have inside versus outside. And molecules want to spread out evenly, the result of which is that they want to go down their gradient. So we're always, when we're thinking about just a simple chemical gradient, going to expect that force to point towards wherever the low is. So in this example that I've drawn, you'd expect sodium to move from the ECF, where there's high concentration, towards the ICF, where there's low concentration. High, lots of packing all packed together, to low, so that they can spread it out more. If you drew lots of sodium inside and only a little bit outside, so you had a high concentration inside and your low concentration outside, you just flip that arrow around. We're always going to go high concentration to low concentration when all we're thinking about is concentration. Questions about this so far? Since we've also talked about membranes, and we've been thinking about what can and can't cross membranes, for the purposes of understanding our topic today, we are going to assume that the cells we're talking about are allowing our solutes to cross the membrane. But on its own, if we don't have any proteins embedded in that membrane, if we don't have any channels, don't have any transporters, sodium, because it's charged, can't cross that phospholipid bilayer, can't cross that hydrophobic region in the center of the cell membrane. So, sodium can only cross if there's some kind of a passageway through. So if you assumed that your cell had open channels, so had some integral membrane proteins letting sodium through, if you have those proteins, it can go. If you don't have any proteins, don't have any open channels, it wouldn't be able to cross. It would just really want to, okay? But you wouldn't see any movement until there's a door, essentially. Okay. Questions about this setup? So that's the basics of where we're starting today. Okay. All right. So when we talk about driving forces and transport across membranes, we're thinking about the fact that sodium wants to go in a direction. We're talking about driving, about pushing or pulling on our molecules because of chemical and physical properties. When I say physical, really what we're going to be thinking about are electrical forces. So in that example that we just drew together, we're looking only at the chemical force. So the chemical force is those concentrations. Okay? So if we talk about the chemical driving force, we're just looking at, is there more of this thing outside? Is there more of it inside? Okay. For the electrical force, we're going to think of those charges. So the fact that sodium is a cation, a positive ion, will matter when we think about the electrical force. So the thing we want to realize about electrical forces are that positive charges and negative charges attract each other. So positive and negative pull together like magnets. And the reverse of that, positive charges and positive charges repel each other. Negative and negative repel each other. So different charges want to come together, like charges want to move apart. To understand the movement of a molecule that has a charge, really we're thinking ions here. Okay? When we're thinking about something that has a charge like an ion, we are going to have to account for both the chemical concentration, this chemical driving force, and the electrical driving force at the same time. So when you have a membrane, you have a separation between the ICF, the intracellular fluid, the cytoplasm, the ECF, say we're intercellular fluid, extracellular fluid. You're going to have differences both in chemical concentrations across that membrane and in some electrical bases. And you're likely going to have some of your ion inside, some of your ion outside. Bless you. But any one ion, right? You pick one sodium out of 1,000 sodiums, any one ion is only going to move in one direction. So when we talk about the electrochemical force, we're trying to figure out, like on net, what direction is that movement going to be? We're not trying to zero out either side. We're just trying to figure out overall, how is our movement going? And this is what is going to build us up into understanding passive transport and active transport. So last time we reviewed, remembering that passive transport happens without energy, active transport happens with energy. To really determine whether we need passive or active transport to happen for a molecule, we're going to need to know what the force is, right? So we're going to need to figure out whether we're moving with the force. If we just let sodium move the direction it wants to go, we don't need to put any energy in, it just wants to do that. Great, we'll let it. But if we want to move sodium or another ion against this electrochemical force, we're going to have to push. We're going to have to push hard. We're going to have to put in some energy, giving us active transport. So fundamentally, when we're determining passive versus active, we want to know about these forces. We're starting with the chemical driving force, which is the example we just drew at the beginning. Okay. So to set up for a chemical driving force, you're going to need a gradient, a concentration gradient. So all that concentration gradient is that you have a difference in how many of that molecule, of that ion, you have inside versus outside your cell. These concentrations are separated. Okay? So essentially, this gradient is just pushing towards wherever the lower concentration is. So we always go high concentration to low concentration for our chemical driving force, which we will refer to in the future when we're abbreviating as the CDF. So chemical driving force, CDF. So you can think of it as this crowd packed together, pushing out. We're just looking at these molecules spreading out until they're evenly spread across, in which case they would be at equilibrium across the membrane. Okay. So the force is from high to low. We will refer to this as down the chemical gradient. So this doesn't always mean outside to inside or inside to outside. It just always means from high to low. So in this case, high to low, the CDF points out. In this case, high to low, CDF points inward, but both directions count as down the gradient because the gradient just means high to low, it doesn't position itself relative to this. Questions about the CDF, this chemical driving force? Hopefully this part you've thought about before in previous courses. An addendum I will mention for our chemical driving force. You will have a chemical driving force for whatever molecule we're thinking about. So it will be true of ions like sodium. It'll also be true of things like glucose, things like oxygen. We'll have a chemical driving force for each of those things. When we think about the electrical driving force, we're really only thinking about ions. So if you have something that doesn't have a plus or a minus sign, you can stop after looking at the chemical. So concentrations are good enough unless you see a little positive or negative charge. Okay. So terminology, just to make sure. Our protons are our charged particles. So ions are ionically bonded. So they either gave away an electron fully or received an electron fully. We have cations with positive charges. We have anions with negative charges. When they're bound together, like NaCl, salt, we wouldn't write a charge on it, but if we put them in water, because water is polar and they're not sharing the electrons, those two ions swap apart and we would end up with Na+, a sodium cation, and Cl-, a chloride anion. Now the part that is going to be new, these are just defining out a lot of the vocabulary terms we're going to be talking about. It's probably the membrane potential. Okay. So when we have a cell, cell, inside, ICF, outside, ECF. I'm not going to draw them on right now. We're going to have some distribution of both anions and cations across the cell membrane. So I'll put some cations inside. I'll put some cations outside. And we'll put some anions inside. Blue. Okay. Bunch of minus signs here, anions inside. And we'll have some anions outside. Okay. So when we talk about the membrane potential, what we're talking about is that these aren't distributed equally on either side of the cell membrane. So if you add up +1 for every plus sign, -1 for every minus sign, on the inside of the cell that I've drawn versus on the outside of the cell I've drawn, you'd end up with something different. So what did I do? So 1, 2, 3, 4, 5, -2, end up with like 3. Okay. And here we have 1, 2, 3 versus 1, 2, 3, 4, 5, 6. All right, great. So if I counted right, you'd end up with -3 inside the cell. So we can do that. We can add up together these charges, and this difference between our -3 and our +3 creates what we think of as a charge separation. So we have a different charge inside the cell versus outside the cell when we add up all of our ions. And this can be a source of energy because this is a force for movement. Because negative charges attract positive ions, positive charges attract negative ions and repel positive ions. And when we talk about the magnitude of that force, we're referring to its strength. So really we're referring to how big that separation is. So if I wanted to increase the magnitude here, I might add more positive ions. Say this goes up to +9, right? There's a greater difference between these two charges. So it would be a greater magnitude. So we'd have a stronger force pushing positive ions in, pulling negative ions out. When we measure these things, we're going to measure it in millivolts. So when you see V, that's millivolts. When you see Vm, that's the membrane potential. So that's telling you about the charge inside the cell. And we do think about it as having a polarity. So basically, all that means is it's going to be either positive or negative, and our reference point is going to be the inside of the cell. For reference right now, because we will talk about this when we talk about neurons, the inside of our cells are usually more negative than the outside, which is why I distributed the charges in that example the way I did, to just get us starting to think about them that way. So usually our membrane potential for just any old random normal cell, so membrane potential Vm, is usually sitting around about -70 millivolts. So MP are our units on that measure. So usually the inside of the cell is more negative than the outside. So the principles for our electrical driving force have to do with this separation of charges. So remember, our opposite charges attract. So positive and minus, positive, plus and minus signs pull together. Okay. Like charges repel, so plus and plus push apart, negative and negative pull apart. When we're thinking about a cell, then what we're going to look at to figure out the direction of our force, we're going to see a cell. We're going to want to know whether that membrane potential, Vm, is positive or negative. So we're going to be looking for a plus or a minus. That's what we refer to as the polarity of the cell. So plus or minus, polarity. And we're also going to need to know, so I'll say on the cell, okay? We're also going to need to know for our particle, so like for our ion, we want to know what this charge is. So we're also looking for whether we have a positive ion, a cation, or a negative ion, and anion. So we're looking for a plus or a minus inside the cell associated with this membrane potential, and we're looking for a plus or a minus on our ion. Because those are the two things that we're going to be thinking of as pulling towards each other or pushing away from each other. So this is just a textbook diagram of what I was talking about with that different distribution of the anions and the cations on either side of the cell membrane. So if this is our plasma membrane in the center here, you can see that on this blue side in the extracellular fluid here, we have more cations. Okay, so plus, plus, plus. On the inside in the intracellular fluid here, we have more anions, minus, minus, minus. And we can see that they can't cross at this point. So they're attracted to each other, but they can't cross the plasma membrane because they are charged particles. So for the electrical driving force, we're looking at the polarity of the cell. So we're looking at, is the cell more negative inside or more positive inside? I said that usually the inside of the cell is negative, which is true. So usually we're at -70. But when we think about firing neurons, firing muscles, what we're going to be doing is varying what that charge is inside the cell. So we do want to be able to understand examples both with a positive charge and with a negative charge inside the cell. And the charge on the particle is going to matter. So we want to think, do we have sodium plus? Do we have potassium plus? Do we have chloride ions that are negative? So we're looking for that charge on the particle. So we're comparing those two things. So here we see a cell that is negative on the inside, and we're looking at an ion that is positive. So our electrical driving force is pulling that positive towards the negative. So we can see this electrical driving force, the EDF, going into the cell. Now in the bottom diagram, we're staying with a negative cell. So we keep our polarity here negative inside. We're looking at a negative ion, so an anion. Okay. What we're looking at here is that negative inside the cell with that negative charge on our anion means that we're going to push that negative out of the cell because our like charge is repelled. And we can see that positive charge, you could also think of it as drawing the negative charge towards it. Okay. So in this previous example, we're pulling towards the negative charge. But we could also compare the positive on the outside and the positive here. It's just when we give ourselves numerical values, all we're going to get a value for is what's inside the cell, essentially. Questions about our setup here for the electrical driving force, the EDF. Okay. We'll let that percolate as we talk. There'll still be time. Okay. So we also want to know that we can change the magnitude of this force, right? So we said that we can have essentially a weaker force or a stronger force. Okay? It's not always just the force is there or the force isn't there. We can change this. So this is going to be based on the strength of the membrane potential. So when we say the strength of the membrane potential, we're talking about, okay, is our charge inside the cell -50 or is it -100, right? -100 is going to be a stronger pull, greater magnitude force on a positive ion. Okay. And we're thinking about the amount of charge on the particle as well. So I like to use sodium a lot because I'm trying to beat that into your heads because we talk about sodium all the time in physiology. It drives like everything that's happening in your body, pretty much. But we will see other ions. Okay. So we also want to know sodium. There's just one little plus sign, but things like calcium. So calcium is 2+. Okay. So that amount of charge on the particle, that valence on the particle, just 1+ or 2+, also makes a difference. So a stronger force can also be created by an ion with a greater charge on it. So those were our two forces separated. So we know if we're thinking about an ion like sodium, we started out by looking at the chemical driving force, which is based on the chemical concentration. We now know that there's also an electrical driving force. So that sodium ion will want to go towards that negative charge inside the cell, or it would be repelled away from a positively charged cell. Okay. But to understand the direction in which sodium ions will travel overall, so on net, we're going to have to look at both those things together. So the total force on an ion will depend on both the chemical driving force and the electrical driving force. So when we think about the full picture, we're thinking about the electrochemical, we just smashed the two words together, driving force. Okay, so that is our E, C, G, F. Okay. So that's all that is. So we're going to sum together the chemical force with the electrical force to get this total electrochemical driving force. So in this example, here in the picture, we see a cell with a negative charge inside. So Vm, our membrane potential, in this example is negative 90 millivolts. We're looking at a potassium ion in this case. So potassium is K+, it's positively charged. Okay, so if we're looking for the direction of our electrical driving force, okay, we're going to be looking at that positive charge on the potassium. We're going to be looking at that negative charge of our membrane potential. Even if the membrane potential is written below the cell, it's still talking about the charge inside the cell. But just so you can see it, Em is always the charge inside. Okay. So that negative charge is going to pull the positively charged ion towards it. So that is our electrical driving force on our potassium ion. But the chemical driving force may not be in the same direction. So our chemical driving force here, we can see we have more potassium ions inside this cell. We have 1, 2, 3, 4, 5, 6. Versus on the outside, we only have 3. Okay. So in this example, our chemical driving force is in the opposite direction. So our chemical driving force is pointing out because those potassium ions want to go from high to low. Okay, so they want to go from their high concentration to their low concentration for the chemical driving force. So we have 2 arrows pointing in opposite directions. If we want to figure out what the electrochemical driving force is, we're going to need to add them up. Okay. In this example, these arrows are the same size. So we're going to assume that these forces have similar magnitude. So we, in this example, would have essentially a force, an electrochemical driving force, and ECDF of 0. Okay. And I'm telling you that just because there's one more number on here, we'll talk about it separately in a separate slide. But when you see this EK number, okay, this is essentially telling you what charge potassium wants the inside of the cell to be. So it wants it to be negative 94, so it actually doesn't really want to move in any direction at all because the cell's already at negative 94. And we'll talk about that in a second. Okay. So when we're thinking about the electrochemical driving force, we're figuring out, okay, what are our concentrations? Where are we going to have our ion or other molecule moving from high concentration to low concentration? What is our electrical driving force? What charges are attracting or repelling each other? Okay. Now, when we do that, we will have our directions. Okay. So if we have a cell, we may see that we have, let's go, high concentration outside, low concentration inside, would give us a CDF pointing in. Okay. So if we're going high, low, that's how we figure out that CDF, chemical driving force. Okay. And let's say we're thinking about sodium or potassium, a positively charged ion. Let's say our cell has a negative polarity, so it's negative on the inside. So if we then draw on our electrical driving force, our EDF. We would want that positive ion to go towards that negative charge inside the cell. So in this example, okay, so I'll write positive and negative just to give us our full notes here. So in this example, both of our forces, both of our separate forces, our chemical driving force and our electrical driving force, are pointing the same direction. They're both sending us into the cell. So it's very easy then to tell that when we add them up, when we look for our electrochemical driving force, it's just going to be in that same direction. So we add them together. So we could go chemical driving force, I did in orange. The electrical driving force, I did in red. Right, so our E, C, D, F, when we add them up, is bigger than each of them because we just added them. So the magnitude of this electrochemical driving force is the sum, the chemical driving force plus the electrical driving force when we add them together. Now, it gets trickier when they're acting in opposite directions. Let's say we'll keep our chemical driving force in that same direction. So for our CDF, we're going to say we have high concentration outside, have low concentration inside. So our CDF points in. Okay. But let's say now we're thinking about a negative ion. Okay. Or we'll get to the or in a second. We're thinking about a negative ion. Bm is negative, our membrane potential is negative, our charge inside the cell. Not gonna give it a number, right? Well, yeah, we can give it the normal -70. Why not? We're thinking about a negative ion, so think about chloride. Okay. So it is repelled by that negative charge. So the direction of the EDF is kind of, that's now our EDF. Our two forces are going in opposite directions. That means to figure out what any one chloride ion is actually going to do, we need to think about which of those forces is stronger. Essentially, which arrow is bigger, which has a bigger difference, essentially. So we're going to take the larger force minus the smaller force to figure that out. So we would take in here the EDF minus the CDF. So if we overlay them, and if those two arrows exactly the same. Okay, so put our CDF here. Okay, we'd end up with a little bit of the EDF left. Right, just that little bit. So we'd end up with a very small electrochemical driving force pointing out in this example as I drew it. But sometimes we'll see a chemical driving force that's stronger. Sometimes we'll see electrical driving forces that are stronger. And if they're both the same size, we'll have a net force, so an electrical chemical driving force of 0. Okay? We basically won't have. So all three of those situations can happen. We kind of pull this question into our warm up with the sodium. So our first part in our sodium example was where we had a chemical gradient across our membrane. We wanted to know whether it could travel across that cell. So our first part was that it wouldn't be able to be transported unless we had a channel protein open. But given our understanding now of the electrochemical driving force, what's another situation where we're not going to have transport across the membrane, where that ion is not going to?
If the electrical force was greater in the other direction.
Yeah, exactly. So if we have a chemical driving force for something to go into the cell, but the electrical driving force is going the opposite direction, pushing it out of the cell, and that electrical driving force is stronger, we're not going to see movement of that ion into the cell, even though that concentration gradient exists. And we wouldn't see any movement at all of that particle if they were equal to each other. Okay? If they're equal, no movement at all. We're going to take a look at some examples of this to make sure we understand all the directions that these forces can go. Okay. So in this example, just going to make sure that we know what these numbers are saying. So up here, we're looking at our sodium concentrations. So that MM is millimoles. Okay, so outside 30 millimoles, inside 30 millimoles. And this number at the bottom, the number in millivolts. Right, and V is our VM, our membrane potential. So we have a membrane potential of positive 50. I want you to think in your head whether sodium is going to move in or out of this cell. So to do this, first, we're going to think about the chemical driving force. What direction is the chemical driving force, the CDF, pointing in this case? It isn't, right? There isn't a chemical driving force because these are equal, right? So concentration inside and outside are the same. There's no chemical driving force. Or we could say the chemical driving force is 0. Okay. In this case, where we have equal concentrations, we do not have to worry at all about the chemical driving force because when we add or subtract it, we're adding or subtracting 0. About the electrical driving force. What do we have for our electrical driving force on sodium? Going into the cell or out of the cell for our electrical driving force. So to do this, remember the two things we're looking at. So we're looking at the charge inside the cell. So the polarity of the membrane potential is how we say that. Polarity of the membrane potential here is positive. And it's also important that we look at the charge on our particle. In this case, we can see that sodium is also positive. In this case, I'm actually going to circle in here to make it a little more obvious. Okay. In this case, we have a positively charged cell, and we're thinking about positively charged sodium. What do we know about like charges? They repel each other. So we're going to have our EDF, our electrical driving force, pointing out. EDF points out because we have that positively charged sodium being pushed out by that positive membrane potential. So in total, when we look for our ECDF, is what we need to know the full direction. We would take our EDF, in this case, some positive, some number going out, EDF, out, right? EDF minus 0 for our CDF. 0. So we get an out for our ECDF. And I'm not going to ask you to calculate like a direct number on that ECDF. We're going to be comparing like which is bigger, which is smaller. But we're not going to worry super much about the exact numbers on. I want us to do one more. I'll keep an eye on that. So now we have a different example, and I want you to take a look at that potassium. We have a new example, we have new concentrations, we have a new membrane potential, new ion. Hopefully, we can predict in this case that potassium is moving out of the cell. So to do that, we saw that we have a concentration gradient now, but our CDF is pointing out. We have the same situation with CDF as we did previously. We still have positive polarity here. We have a positive charge on our membrane potential. Potassium is also a cation, a positively charged ion. So our EDF also points out. Okay. So our total, our ECDF, is going to be up. So, okay. So let's try an ion, so a negatively charged ion, to make sure that we can do this with all sorts of different charges. In this case, we've changed that charge on our ion, but now our cell doesn't have a charge in it at all. So our ECDF will just point with the concentration gradient. Goes in, okay. But if we were to have a positive charge like we did before, right, so we had positive 50 on one of the previous examples, that would create a pull on the chloride towards it, right? Or if we had our usual negative 70, that would push chloride away from it. So we can do this with positive and negative numbers. But pick up next time talking about the equilibrium potential. You want to do that and that's whether up to an SI. On that.